The second discrete probability distribution we're going to discuss, theoretical discrete probability distribution, is Poisson distribution. Poisson distribution is when you are interested in the number of times a particular event occurs in a given opportunity, area of opportunity. Okay. Area of opportunity can be a time interval, like time between noon and 1 o'clock, how many customers will walk into the bank, for example, during lunchtime. So area of opportunity there is really a time interval, or it could be how many defects are there in a square yard of a carpet. Yeah. So here it is our area of opportunity is literally an area. So it should be the area of opportunity is an interval of time or volume or area that is continuous. Okay. And then within that area of opportunity, okay, you count a certain outcome. Okay, and you could call that success. You are counting how many success. So here, the number of scratches in a car's paint. So car's exterior is the area of opportunity, and now you're counting how many success. Here, success, okay, again remember, success in quotation marks is scratches. So the number of mosquito bites on a person's body is then the area of opportunity, and number of bites is the success that you're counting. So the number of computer crashes in a day. So now a day is your area of opportunity, and the number of times the computer crashes is what you're counting, and that's your success. So if this is true, okay, then we can apply Poisson distribution to compute probability of those events, like how many successes there is going to be. So x equal to 0. So if you're talking about number of mosquito bites on a person's body, it could be 0, 1, 2, 3, and on and on and on. It is a countable infinity of possibilities. Okay. Now we want a probability of 0 or 1, 2, 3, 4, and on and on and on. Now that probability can be computed if, okay, you have the average number of events, average number of success in one time unit. So for example, if you're talking about one day, how many computers are crashing, or one person's body and how many mosquito bites are there. So if you need to have the average for that event. So on the average, how many computers crash in one day, or on the average, how many mosquito bites you will find. Okay. Once you have that average, then we can compute probability for individual outcomes. So you wish to count the number of times an event occurs, and you want the probability for that each outcome, and then you need this average number, and let's call that lambda. In Poisson distribution terminology, we use lambda to stand for the average number of events or average number of successes in one unit of the area of opportunity. So then the probability under Poisson distribution is given by this formula. So probability of x given lambda is the average number. Okay, so you need now a constant called like pi. Pi is a constant, right? So like that, you have e is a constant, and the value is approximately this. So e to the power of minus lambda, lambda to the power of x, divided by x factorial will give you that probability if it follows Poisson distribution. So, and the mean and standard deviation for a Poisson distribution is the mean is simply lambda itself, because that's how we defined it. So average number of outcomes in the per unit of opportunity, area of opportunity. Now variance is given by lambda also, and therefore standard deviation is square root of lambda. Okay. So we have Poisson table available. Poisson table is not in the textbook, it is available online. You can download the Poisson table, and then you have different lambdas here and different values of x, and you can use the table to find the probability, or you can use the formula, or you can, in Excel there is a function for Poisson probability, so you can use the Poisson probability function. So we'll use the formula and the Poisson function in Excel. Now if you compute the probability of all possible values of x and plot them, and this is what the Poisson probability distribution function will look like. Of course, you remember as x increases and increases, the probability asymptotically reduces close to zero. See, it never actually goes to perfect zero, because in Poisson distribution you can count x on and on and on to infinity. So it is a countable infinity. So there is no upper limit for x. So the probability only reduces and reduces asymptotically to zero. So here are some approximate shapes when lambdas are different. So lambda of 0.5, this is what the shape will be like. Lambda of 3. So it starts as lambda increases, you tend to get closer and closer to a kind of a normal distribution or a bell-shaped distribution.